So this idea of Lenz's law is a little bit confusing until you get used to it. So let's take a look at what Lenz's law says. It says a current produced by an induced EMF moves in a direction so that the magnetic field created by that current opposes the original change in flux. So the word here that we want to highlight is opposes. Also, it's defined an induced EMF is always in a direction that opposes the original change in flux that caused it. And how do we get this? Well, it's in Faraday's law. It's a little innocuous, but it's there. And this negative sign is Lenz's law. Looks pretty innocuous, but it does mean a lot. And let's see how that works. And we're going to look at an electronic circuit. So it's we're going to relate the flux in the this coil, this inductor, to a current. But I think it'll make the point for us here. So at the start, there's a 12 volt potential here. So there's plus 12 volts. So the current would flow up this direction through the resistor R1, and then you're going to get current flowing through resistor R3. And once I close the switch, I'm going to have a current that flows through the capacitor and the inductor. So let's look at the capacitor. When the current flows into the capacitor, it produces a positive charge on the top and negative charge on the bottom, and it's going to charge to 12 volts. And we can see that here with this charging curve. We've discussed this curve before. But the inductor, what it does is when the current flows through, it's going to create a flux, and that flux is going to try to keep the 0 amps flowing through there that was originally there when the switch was closed. And so it's going to induce a potential to fight that. So it wants to keep it at 0 amps. So it's going to create an induced potential across it for an instantaneous time, and then eventually it's going to jump up, and then it's slowly going to reduce down. So this induced potential is what we're talking about for Lenz's law. It is opposing this change in current, this change in flux. Now, when I go to discharge, well, let me erase a few things here. So now we close the switch, and for the capacitor, when I close the switch, well, this 12 volt potential is across the capacitor. You cannot change energy instantaneously. It's impossible. Can't do it. And so the capacitor stores energy stores energy in the electric field. And because it stores energy in the electric field, you can't cause this potential to go down instantly. There's charge here, and that charge has to bleed off, so to speak. And so when I make this connection with the switch and put it in parallel with this 1 ohm resistor, we know that the charge is going to flow in a current in the counterclockwise direction until it decreases, as we see in the picture here, down to 0. For an inductor or a coil, it stores energy in the magnetic field. And since it's the magnetic field, you cannot change the current instantly. So when there's a current flowing through, in this case, there was a current flowing through, and we know that current would be, if at the end this looks just like a short, so there would be current flowing through it, this looks like a short, then I know that my current is going to be 12 volts divided by 1 ohm. That's going to be 12 amps of current. And so now, once I flip this switch, this current, this inductor is going to want to maintain that current. So before I had this as plus and minus, and that was 12 volts. The instant that I throw this switch, the inductor changes its polarity instantly to keep this current flowing in this direction. And so if the current's flowing in this direction, then that means this is going to act like a battery or source, and my polarities change. And in this case, it's going to be 12 volts, because it's going to take 12 volts to put 12 amps of current through a 1 ohm resistor. And so as you can see here in the chart, the polarity changes. And at the first spike it was 12 volts up, a positive, which we saw because it would oppose the current and it would need 12 volts to do that. And when you flip the switch and there's 12 amps of current flowing through this inductor, it needs to produce or induce a 12 volt potential, but it's going to be negative so that it can keep the current flowing in the same direction. Now, if I were to change this resistor to 2 ohms, well, what would happen is that the induced potential to keep that 12 amps flowing would increase to 24 amps. I'm sorry, 24 volts. In the direction. So it only took 12 volts to resist the change, and then it died out. But to keep the current at 12 amps, it's through a 2 ohm resistor, it's going to have to double the potential to keep that going. So an inductor will do whatever it has to do to maintain this current flowing in the direction that you try to change. And so this is the idea of Lenz's law. And so if we take a look at a capacitor and an inductor. And an inductor. We'll talk about inductors next chapter, but for this case, we'll just talk about it as a coil or a loop. Then the idea is this: if I have voltage potential and current, for a capacitor, it can't change instantaneously. But the current can change. It can change direction instantaneously. For an inductor, it can change the polarity instantaneously, but it can't change the current instantaneously. And so these relationships make it so that we call the capacitor and the coil dualities. They have similar properties with voltage and current. They just end up being reversed, right? But these are very important concepts, and it's this idea of Lenz's law that we need to keep in mind, how things go to keep the current flowing in the same direction. Capacitors are fairly easy to understand. Lenz's law, this is where we are going to have to make sure that we keep track of what's happening so that we can get the correct potentials in the right directions.